Yeah, good afternoon, good evening, everybody. Welcome. It's EMinar Wednesday, and it gives me great pleasure to have Neesha Schnepf talk to us today on EM induction from tsunamis. I'll introduce Neesha in a moment, and just as people are rolling in, quickly remind people, those of you who came to the EMinar a different way, if you want to see past EMinars or upcoming ones, just go onto the MTNet webpage, and the link's down here. And there you'll find links to prior EMinars, recordings of prior EMinars and presentations, and registration links for upcoming EMinars. Next week, we have a rather special one. It's I've got a few invited speakers coming from industry and from academia who are going to talk about empty equipment. And there's a picture of some empty equipment that I cut my teeth on in the early 70s. So we have instrument manufacturers, and we also have instrument users. Some companies will be speaking about novel data acquisition methods. But today we have Neesha Schnepf, who will talk to us on EM induction from tsunamis and the January 15th, 2022 Tonga eruption and volcanic eruptions generally. So Neesha has done a bachelor's at Cornell in 2013, master's at MIT, PhD, University of Colorado, so an absolutely stellar background. Was a postdoc at NOAA's National Center for Environmental Information, and then worked at Maxar Technologies as a data scientist. Now working as a research scientist at Colorado's lab, and Neesha pursues research questions related to planetary fields and habitability. So that, I'll stop my share, Neesha, and invite you to come in and give us your EMinar.
Okay, so is that sharing all right?
Yep.
Okay, great. Okay, let me just move that. Okay, great. Yeah, so thanks. So today I'll be talking about electromagnetic induction, especially magnetic fields, from tsunamis and submarine volcanic eruptions. And like Alan said, I'm at the University of Colorado's Laboratory for Atmospheric and Space Physics. I'm fine with both they and she pronouns. You can't go wrong, basically. And so, yeah, let's get into it. So the main motivation for this work comes from two really dramatic events. The first one being the March 11th, 2011 Tohoku tsunami. And these are just some videos that showed how dramatic and frankly terrifying the tsunami was. It arose from the most powerful earthquake ever recorded in Japan and the fourth most powerful earthquake in the world since modern record keeping began in 1900. It was an M9.0 earthquake. And the tsunami from this earthquake, it wound up hitting the coast really quickly. So the town of Sendai only had about 8 to 10 minutes of warning. And then the second star to the south here is where there was the Fukushima nuclear power plant, which had that horrible disaster. And I'm just sharing these two bullets to really drive in that every minute of warning time can make a huge difference in trying to ameliorate what happens a bit. This particular event really had a huge human toll. There were almost 20,000 deaths, over 6,000 people injured, over 2,500 people missing, and a few years after the tsunami, there were still over 200,000 people displaced. So that's like a little more than half the state of Wyoming, right? Like still displaced. So this is the tsunamis whose magnetic fields have been the most studied, and has just inspired most of the work in looking at magnetic fields, electromagnetic fields induced by tsunamis. And now the other big event happened at the start of last year. So on January 15th, 2022, in Hunga Tonga Islands, there was a submarine volcanic eruption, and probably you've already seen this really compelling video. On the volcanic explosivity index, this was a 5, which basically means very large. The eruption displaced 10 cubic kilometers of rock, ash, and sediment. And it was the largest atmospheric explosion recorded by modern instrumentation. The shockwave from this eruption sonic boom was heard even in Alaska. So that's over 9,000 kilometers away. It took 9 hours for this sonic boom to get there, but when it got there, it was still audible. So the human toll for this disaster wasn't quite as dramatic because it did happen in the middle of the Pacific, but there were some injuries, missing folks in Tonga, and there were deaths both in Tonga and actually all the way in Peru, resulting from the tsunami. So these two really extreme, powerful natural disasters are like what motivates this line of research. And the main question is pretty general. It's just what magnetic signals can we identify in these events? And then related to that, like, can we use those magnetic fields to better understand the geophysical processes occurring here? Or can we use those magnetic fields in our actual warning systems? So now I'm going to shift gears a little to make sure everyone who's attending this is on the same page, because I know most people, right, who attend the EMinars have a magnetotellurics background. So you're used to thinking about these broadband external magnetic fields and using those with your electric field and magnetic field tensors to probe into the physical Earth. Instead, here I'm going to be talking about electromagnetic induction from electrically conductive fluids like the ocean, but also from the ionosphere. So it's a different approach to electromagnetic induction. And the starting point is the ocean. So most of our planet's surface is covered in a fluid that's always electrically conductive, right? Salt water is electrically conductive material. And because it's flowing through the Earth's main field, it creates electric currents, which in turn induce electric and magnetic fields. And I try to avoid equations, but I think in this case, this equation can help make what's going on more intuitive. So this is the electric current from ocean flow. So this first term here is the seawater's electrical conductivity. And globally on Earth, this has an average value of 3.31 Siemens per meter. The next term is the velocity of ocean flow. And so this ocean flow, this velocity term can be from any type of ocean flow. It can be from tides, circulation, or tsunamis. And it's crossed with the background magnetic field, which here is Earth's core magnetic field. And this is pretty well known, right? We can use the IGRF or WMM model to have this source term. So if you're more of a visual learner, I have this cartoon that also walks through marine electromagnetic induction. So we have the Earth and the main field. Then we can go to the oceans. We have a wave traveling with this velocity u, and the seawater has this electrical conductivity. The Earth's main field is pointing down. If you recall the Lorentz force, right, we can use the right-hand rule. So the velocity going this way, field going that way, it's going to induce an electric current that goes inwards along that wave flow. So that's this electric current here. Now, if you remember Ampere's law, whenever you have an electric current, that induces a magnetic field that, again, you can use the right-hand rule, and that magnetic field will wrap around the electric current. So we wind up with the ocean flow magnetic field that I depict here in green of like BZ and BH. So yeah, this is how the ocean induces magnetic fields, and you'll note, right, like it always is happening. Like whenever the ocean's moving, this process is happening. So this is different than magnetic fields from the ionosphere, for instance, where that depends on solar ionization. Yeah, so we can look at oceanic magnetic fields using satellite magnetometers or observatory magnetometers. And the ocean field, we can decompose it into two components, right? So a horizontal field, which you can also think of as a toroidal field, And this field is mostly limited to within the ocean because the magnetic field decays as 1/r². So to really measure this field, you need your observatory to actually be on the seafloor. Then we have the poloidal fields, which you can also think of as BZ. So these are the fields that go beyond the ocean, and these are the fields that we detect when we're using island or coastal observatories or satellite magnetometers. Okay, so the ionosphere, right, its electrical conductivity depends on solar ionization, it's time of day dependent. The ocean, instead, its electrical conductivity depends on salinity and temperature. Magnetic fields in the ionosphere can be driven by neutral waves. In the ocean, there's no separation of like neutral fluid and non-neutral fluid, right? All ocean water is electrically conductive, and so it's driven by all types of ocean flow. And at a ground observatory, oceanic magnetic fields are internal, the ionospheric magnetic fields are external. So this can sometimes enable separating the field sources. And so this is my segue into just, right, reminding all the different magnetic field sources, right? Like we have magnetic, how does this, like when we care about the magnetic fields induced by the ocean, we need to be really careful that we're actually correctly isolating them, right? That the signals we're looking at aren't actually just coming from some other part of the geomagnetic system. So most of the field here comes from the outer core, right? The core field is the dominating signal. The next is the magnetospheric field, which is about 3 orders of magnitude weaker than the core field. And then next up, ionospheric field. Sometimes the crust can have strong magnetic fields, and then you'll see the ocean's magnetic field is the weakest in terms of strength, right? About 2 nanoteslas. So this can be a bit of a needle in a haystack. But I like to just remind people, right? Like whenever we measure magnetic fields, we're measuring the superposition of the fields from all these different sources. So we can take advantage of the different sources fields having different characteristics, like different wavelengths or periods, and maybe different spatial characteristics, and use these with different mathematical techniques to then separate out the source that we're interested in. Yeah, so, okay. So moving on for now, we can now focus a bit more on tsunami magnetic fields. So for the tsunami flow in particular, right, this is a water wave that propagates out from an epicenter. So this is the same cartoon I showed you before, basically, but now we can also look at it in this top-down view, right? Epicenter, the wavefront's expanding out. And again, like when you do the right-hand rule on this, you'll see like you have an electric current that goes along this wavefront. So it induces a magnetic field that basically travels with the wavefront. So this is sometimes referred to as a frozen-in magnetic field. So the field overall, it's dominated by that magnetic field. You can also have a self-induction contribution, right, from the change in magnetic field with time. But for most cases, that is a much smaller contribution than just that basic Lorentz force field that I show in this cartoon. Okay, so Rob Tyler's 2005 paper was sort of the start of kicking off interest in looking at tsunami magnetic fields. He did theoretical work where he showed that the tsunami's induced magnetic field compared to the main field will vary directly with the tsunami's sea surface height relative to the ocean depth. So he was arguing if you're able to measure the tsunami's induced magnetic field, you can then learn these other parameters about the tsunami. And in his paper, he basically argued that you can determine tsunami velocity vector from one observatory's vector magnetic field observations. You'll notice, so what I have in the background here is actually a dart buoy. This is the way we currently determine tsunami velocity vectors. We have, like NOAA deploys a network of these buoys, and you need multiple buoys to determine tsunami velocity vector. So this paper really kicked off excitement because people were like, oh, if we can use one magnetometer giving us vector magnetic field data to get tsunami to get the tsunami velocity vector, like that could actually be more useful for tsunami warning systems instead of needing a network of dart buoys. And then since then, Manoj led actually observing the tsunami magnetic field from the February 27th, 2010 Chilean earthquake. So this earthquake was a magnitude 8.8, so it was quite big. And the picture I have here is from a bit more recent work, but you can still see that there was a pretty clear tsunami magnetic field with the water wave arrival at these seafloor magnetometers. And then, like I already motivated, when the Tohoku tsunami happened, that led to a lot of interest and a lot of work on this field. And one of the biggest discoveries was that the tsunami magnetic field can actually arrive before the tsunami water wave by like 4 to 20 minutes, depending on the study you're looking at. So I'm going to first go through a bit of what Takuto Minami predicted. So in the deep ocean, right, a tsunami wave has a really long wavelength, and it travels with a speed comparable to a jet plane. And then as it approaches land, because the water column becomes more shallow, that wave gets compressed, the wavelength gets shorter, and the amplitude gets much bigger, right? So that's why when it hits, the coastal town, you have this huge wave that's hitting. And so Takuto argued that the tsunami magnetic field is also going to depend on the ocean depth. And in his predictive work, he basically established that there's going to be these different regimes. So when the tsunami is in the shallow water, it'll be the diffusion dominant regime. And the main thing to take away here is that the tsunami magnetic field will really follow like what I've already walked you through. It'll be dominated by that Lorentz force where the magnetic field is just traveling with the tsunami. But then he argued in the deep ocean, right, where the wavelength is comparable, or where the ocean depth is much, or sorry, where the wavelength to ocean depth ratio is like different because the ocean's so deep. Basically, it's going to be a case where the self-induction term actually really matters. And so what you have happening here is as the tsunami is propagating, there'll be a horizontal, like it will induce a horizontal electric field, which leads to that self-induction horizontal magnetic field. So you wind up having this magnetic field getting induced like a little before the water wave. And so depending on how dominant that is, will change like how much that induced magnetic field leads the water wave. And then a few months after he published this predictive work, Tate Hata and his colleagues like published a first look of this phenomenon with the Tohoku tsunami. So here they're comparing the tide gauge record at Shishijima Island and the Shishijima Island magnetic field data. And you'll see like this, so this triangle is denoting the arrival. And they found a 20-minute difference between the vertical magnetic field arrival and the tide gauge water arrival. And so I should say there is a little bit of some nuance here too, because I believe the tide gauge and magnetometer are at some different locations on the island's bay. So this like preceding arrival is a bit exaggerated here. But even then, right, this was obviously very exciting to see because 20 minutes is just a really dramatic early arrival. Oh, yeah. Okay. And then in work that I did, also looking at this, this was part of my PhD work, and I was looking at the signal in terms of its time and frequency characteristics. So looking at the different periods as they were actually occurring. And so I found that the portion of the signal that's arriving earliest is related to the longer period portion of the signal. So basically this is happening both because of the self-induction term and because of dispersion of the tsunami magnetic signals. So that's enabling this earlier arrival. But yeah, so of course then the main question is, can we actually use these magnetic signals? Like, can we use this earlier arriving magnetic fields in tsunami warning systems? So there's one challenge, like I'm gonna walk through just a few challenges here. The first is Earth's main field term, right? The tsunami's velocity is dominated by the horizontal flow. So in this cross product, the Earth's vertical field is what most matters, right? But if we look at a map of the Earth's main field's vertical component, right, you'll remember here along the magnetic equator, this term goes to 0. So, a lot of people were like, well, this would suggest that for huge swaths of the ocean, this isn't going to really be a reliable way to like detect tsunamis because their induced field is going to be so weak. But again, Tohoku led some numerical work, and basically the magnetic fields generated by tsunamis can have primary and secondary arrivals, and we compare them to seismic waves mostly because that's just fun. It's the flashy comparison everyone's already familiar with, right? When an earthquake happens, you have this P wave and then an S wave arrival. And instead, we're saying that you'll first see a magnetic field arrival from the horizontal component and then a field arrival from the vertical. And on this cartoon, right, I drew in the horizontal field here and vertical field here to just convey that this vertical field is much larger in amplitude than the horizontal field. So this term matters mostly when you are near the magnetic equator, because in those areas, this component will become much more decreased. But yeah, so this is a bit promising because it means if we're trying to detect a tsunami in this region, it will still be possible because we can use this horizontal field. Okay, now the other main challenge is just the actual engineering and logistics of real-time tsunami detection. So for a very long time, Hiroaki To of the University of Kyoto was running the Northwestern Pacific seafloor magnetometer that I show here. And for a long time, it was the only near continuous and near real-time seafloor geomagnetic observatory. It's no longer actually deployed on the seafloor, and we're trying to figure out a way to deploy another long-term seafloor magnetometer. So along with, those aspects of actually getting a seafloor magnetometer, all the methods, right, like all the studies where we've looked at tsunami magnetic fields, we were using data in the past and using time and frequency methods that, work for looking at past time data rather than actual real-time data. So there needs to be ongoing work or future work to actually develop like real-time techniques for reliable tsunami identification. And so for that front, I say stay tuned because both of these are works in progress. And now the third challenge is that any event has to be, to have a detectable magnetic field for tsunami, the event has to be quite big. So these are, again, from paper from my PhD work, and these were the smallest earthquakes where we saw detectable magnetic fields for the tsunamis, and they both are still above a magnitude 8. So that's a really big earthquake still. And so, yeah, like part of the challenge here is just the data availability and just the frequency of events that are actually large enough to make to induce a magnetic field that we can detect. Okay, so now I'm going to switch gears a little bit and talk about magnetic signatures from the Hunga Tonga Hunga eruption. And yeah, this was a very big event that had led to magnetic signals in both tsunami water waves and from atmospheric waves. And as far as I know, it was the first time of trying to look at magnetic fields from a submarine volcanic eruption. So this is a cartoon to just slowly illustrate the major different types of magnetic fields that arose from this eruption. Okay, so first, the eruption sent shock waves propagating through the neutral atmosphere. And these waves eventually reached the ionosphere, and that led to these external magnetic fields, right? So if this is the observatory, these are external magnetic fields. Meanwhile, these shock waves also interacted with the surface of the ocean. So there was sea surface deformation by these atmospheric waves, and this is actually known as a tsunami. So we have an internal magnetic field induced by this tsunami's ocean flow. And then there was also shock waves just directly propagating in the ocean. So we also have just classical tsunami traveling as well, also leading to these internal magnetic fields. So yeah, there's 3 different types of signals all arising from this eruption. So we looked at data from 10 intermagnet observatories. I show them here on this map, and the star is the eruption site. Red is for the like I'm kind of cheating and just telling you already in red. Like these are the observatories where we believe we saw signals from this eruption. And I'm looking at both the vertical component and horizontal component. And one of the challenges here is that this was a fairly geomagnetically disturbed day. The hours that sort of start when the eruption happened, and then for a few hours, it became much quieter. So that's good at least. But well, you'll see when I show some of the results, like it was a more challenging day to try to look for induced signals. But I included this particular station, so Alice Springs in Australia, since it's in the middle of the desert, doing cross wavelet analysis with island observatories. It shouldn't, like the only overlap between the observatories should be from external magnetic fields and not like the local ocean fields, right? Since the station is both so far away and in a desert. So yeah, we'll start with the API Samoan station. Okay, so what I'm showing here is data that's gone through a high pass filter, both with a max period of 30 minutes and a max period of 2 hours. So traditionally, when looking for tsunami magnetic fields, like we'll just use a max period of 30 minutes because that covers most of your tsunami like wavelengths. But because this is an eruption, we realized we needed to include longer periods. And so A and C, both of these panels are showing the water height variations at this island. And then these 2 panels are showing the vertical magnetic field. And I also looked at the horizontal. I didn't include it here in this presentation, but you'll see, and so in both of these vertical fields, there's these really high frequency signals that arose. They were also in the horizontal field as well. And if we do this, look at the cross wavelet spectrograms, you can see that for this region, Western Samoa was the only observatory to have these sorts of high frequency signals. And this dashed line is showing when that water wave reached the island. So, okay. Yeah, let me just do that. Okay. And then this is just a thing to note, right? We see this anomaly at the New Zealand Observatory, then Canterbury, then Charter Towers. So I just would be curious to know if this was related to a traveling ionospheric disturbance, because it looks like it could have been. But coming back to the Western Samoa signal, so these high frequency signals were both in the vertical and horizontal components. So in that way, we can pretty much rule out that it's from a tsunami because, like I said before, the oceanic horizontal field gets attenuated before reaching land. And so this site was studied by some other folks last year. And so Yamazaki and colleagues, they also saw these high frequency signals. And Okay, so they argue that it's actually the signals are consistent with the atmospheric oscillation due to acoustic waves trapped between the ground and the thermosphere, or an acoustic resonance at this frequency. So basically, they're arguing like along this field line that goes over the eruption near the observatory towards its magnetic conjugate, it can lead to a resonance in the ionospheric waves that gives this really high frequency signal near the site. And I believe this was seen with previous volcanic eruptions. So that was just kind of cool, I thought, that this was seen. I have a little tangent here because Hiroaki told me that this observatory is actually in danger of being removed. So this is where the observatory is, and there's a lot of government buildings here, and apparently they want to build a government building like right where the observatory is. So, you know, if this work compels you, or if you already care about this observatory, I strongly encourage you, hang on, let me move, to reach out to the both the lead for the observatory and for Samoa's meteorological division to argue that they should either preserve this observatory or maintain some other observatory if they go forward with the construction. So this is a bit of a tangent, but these results, I think having this observatory is really important since, right, the Pacific is so big and there's so few observatories. But yeah, so it had the strongest signals from this eruption event as well. But yeah, Alan will have this posted online so you can get this contact info again. But now we will move towards Easter Island. Okay, so here, this is the same sort of setup, maximum period of 30 minutes versus 20 minutes, water wave, magnetic field, water wave, magnetic field. So what was interesting here, when we just go up to 30 minutes, there weren't any clear signals. But when we expanded up to 120 max period, we saw this signal of about like 90-minute period in the vertical component. It was only visible in the vertical component. Looking at the cross wavelet spectrograms for these three observatories, we can see that they each seem to have similar signals, even though like their water wave arrival from this event is quite different. Only at Easter Island does it seem to coincide with the water wave arrival, but I would guess that that's probably just coincident and that these are likely external in nature. So yeah, it's more likely to be from some sort of ionospheric propagating shock wave. Okay, and now we'll come over towards Japan. So Red is Shishijima Island, and this is the same observatory that was very well studied for the Tohoku event. And things get a little funky here. So if we are looking at a maximum period of 30 minutes, we can see, like, I mean, it seems like there's waves arriving here, but the magnetic field is fairly disturbed before this time, right? When we filter the data with a max period of up to 120 minutes, then in the water height variation data, we see something really interesting, right? Like it's fairly quiet. Then at about 11 UTC, there's this arrival that's similar to the arrival for max period of 30 minutes. But then there's another arrival around 1325 UTC, right? Like the amplitude almost doubles. And so some other studies confirm that this is actually the arrival of the Meteo tsunami, and then this is the arrival of the like classic tsunami. And so we're doing further investigations now to see if these magnetic fields, which seem really comparable to the classic tsunami arrival, are indeed that, from the classic tsunami, and if we can instead see signals also from this meteo tsunami or other atmospheric waves. But for now, right, so if on top, I'm maintaining this wave height variation. So as we look at the cross wavelet spectrograms, you can kind of keep in mind like meteo tsunami arrival versus tsunami arrival. And for Shishijima, right, the strongest magnetic signals coincide with the classic tsunami's arrival. But when we look at the observatories in the rest of Japan, which also I should just say these other observatories, I know on this map, they seem as if they're like right on the ocean, but they're actually inland quite a bit. So we wouldn't expect tsunami signals to be visible here. So whatever we see here, we would expect to be from the ionosphere. And well, we see a lot happening, right? Like there's a lot of signals at these other observatories, and there's a fair bit of similarities with what we see at Shishijima Island. So yeah, like we can say at Shishijima Island, the magnetic signals are in the period range of 13 and 19 minutes, which is completely aligned with what we've seen in other tsunami studies, but there's so much activity happening here. And so we have ongoing work to keep trying to separate out the different contributions here from the tsunami and meteo tsunami and other atmospheric waves. And hang on, yeah, okay. So the plug here is that Takuto Minami will be presenting some updated results at IUGG in July. So if you're going to IUGG, you can kind of see what we tease out a bit more there. But otherwise, my summary for this event is that we saw really short period high frequency signals at Western Samoa, which were consistent with other studies and would indicate an ionospheric magnetic field resonance. Longer period signals of like 60 to 90 minutes at Easter Island and some of these other Eastern Pacific observatories. And then magnetic signals more like what you would expect for a tsunami at Shishijima Island, but with a lot of noise or other activity we still need to sort out. And I included this diagram that shows the different atmospheric pressure waveforms. So there's co-volcanic ionospheric disturbances that have propagated out, and they can have periods similar to tsunamis. So I just would be really curious for future work to look at whether or not we can correlate some of the magnetic anomalies I've just showed you to some of these traveling ionospheric disturbances. Okay, so summary for both of these events and just the big picture. We can detect magnetic signals from tsunamis, meteotsunamis, ionospheric disturbances. Now, can we use those magnetic fields to better understand the geophysical processes occurring here? So magnetic fields are incorporated into tsunami source studies. So I believe they can help clarify that some, but there's a lot more work that we need to still improve our understanding of the different external and internal sources at play for like post-eruption magnetic fields like I just showed you. And can we incorporate magnetic fields into warning systems? Well, we need both the long-term seafloor observatories to do that, and we need to convert our different time and frequency methods to work in the real time. And so a little bit more on this outlook here for the long-term seafloor observatory. I've been chatting with the different folks about this, and I guess I just wanted to include a little teaser to something Hiroto and I are looking into. The National Science Foundation has this Ocean Observatories Initiative where they actually have this regional cabled array off the coast of Oregon. So all of this cable that you see both going out to the seamount and winding around here on the continental shelf. It's over 900 kilometers of cable. It already has over 140 different instruments attached to it, including many different pressure sensors and seafloor seismometers. And they even have a couple electrometers for electric field measurements. So we're in discussions with these folks to figure out what it would take to add some long-term seafloor magnetometers to this array. And the idea here is that then we could actually have, right, some long-term observatories for doing more studies in this field. So this seamount is pretty active, so that could be useful for more studies on the electromagnetic induction of volcanoes. And then there was another study that found over 40 tsunamis in a 30-year time period in this region. So this region might also be fantastic for more magnetic fields, tsunami magnetic field studies. And then of course, other more traditional electromagnetic sensing purposes. So yeah, so just including this, right? Volcanic studies and also maybe tsunami studies. So hope to have updates on this in the future. But with that, I'm happy to have this switch over to be more of questions and discussion. So thank you for listening.
Yeah, thanks very much, Neesha. Absolutely fabulous. I really like to see these the work we can do as EM scientists that have societal implications. GIC work, space weather work we're doing, and now this type of work, particularly if we can protect people's lives using our methods. Just a quick question while others roll in. Please send your questions in the Q&A. So looking at this explanation of the high frequency ionospheric field resonance, it looked like the field line was going right past the Honolulu station. Was it not seen on the Honolulu station as well?
It's apparently just far enough that at Honolulu, I instead only saw these longer period signals.
Okay.
Yeah.
I guess the other question is, now you've got this image up, is was there no tsunami observed in French Polynesia? Is that the problem? Why there's the PPT site is?
Yeah, I was actually also surprised that we didn't see a tsunami there. And I don't have an explanation for that.
Yeah, I was just wondering whether the shape of all the different islands meant that there was such there was perhaps constructive and destructive interference, so there wasn't a sufficiently strong tsunami.
Yeah,
as you said, it's quite strong, right, to generate.
I think the tsunami just maybe wasn't strong enough. I remember like at the time that we were putting this paper together, I wound up like really digging in on Google Earth, looking at exactly where each observatory was to see how close it actually was to the coast. Because like for Honolulu, for instance, I remember when I looked it up, I was like, oh, if the tsunami was too weak, where that observatory is located, definitely some of the anthropogenic noise around it could have completely prevented being able to detect that signal. For Tahiti, I'm not totally sure, but I think it does just come down to the tsunami wasn't strong enough.
Yeah, it's ironic, normally the people who do global EM induction studies complain that too many observatories are at coastlines and they have to deal with all the very strange effects on coastlines, and yet you want them there.
Yeah, I want them there. Or, I mean, most ideal would be on the seafloor, but yeah.
So we have a question from Anne Sheehan. Have you compared the tsunami magnetic signals to GNSS-derived ionospheric TEC detection of tsunamis?
Yeah, so TEC is the total electron content, and I have not done that, but that is something I really want to do, is partner up with an ionospheric person with expertise in TEC data sets, and like there are several folks who've been looking at TEC disturbances from this eruption, and then also probably from Tohoku, and see like what magnetic anomalies correlate with the TEC disturbances they've seen.
Yeah, well, you've got an in. Anne looks interested.
Yeah.
Are there any other questions for Neesha? I think this field was so different for most people that they're struggling to think of questions to ask.
Yeah, that's fine. We had one come in.
Salima says, thank you for the presentation. My question, how much magnetic stations are needed for an early warning tsunami system?
Yeah, so
Yeah,
this is definitely a question that comes up quite a bit. Because like theoretically, right, we just need one observatory with a fluxgate magnetometer to then constrain the tsunami's vector field. But of course, the big caveat there, right, is that we need the tsunami to actually travel over that magnetometer, right? So we need some kind of coverage. Hang on. Oh, I need to come here, I guess. I was like, I want my cursor to go on the presentation. It's not. Well, anyways, I guess you can just look at this map of the ocean, right? And I think this is definitely an area that future work could be done in, right? Using like maybe Tokudo's tsunami models or other folks' tsunami propagating models to figure out like what's the minimum number of observatories needed across ocean basins where you have the highest probability of detecting any type of tsunami that would happen or be likely to happen. Because I guess, right, without that type of study, my intuition is just that we would need at least one in every major ocean basin.
Yeah. Depends where it originates, of course, because to be useful as a early warning system, you want them all over the basin, right?
Yeah.
Okay. If there's no more questions, I know that Neesha, you have to dash off anyway, so perhaps we'll let you finish and get to the next appointment. And I'd like to.
That's good.
Anonymous attendee says thank you. So thanks, Neesha. Wonderful presentation. This will be up live shortly when I get the recording from Zoom. And Neesha sent me a PowerPoint that'll be up on the MTNet. So thanks, everybody. Thank you, Neesha. And bye. See you next week.
Yep. Thank you.